105, yes. All right, this is going on page 105. When we are done, we are looking at trigonometry and the polar coordinates. So I'm not going to read all of this to you. You can go back and read it at your leisure if you want to, but I'm just going to kind of sum it up for you. So if we are going to travel from one location to another, we can ride our bicycle, we can drive a car, we can drive a boat, we can fly a plane, just kind of depending on where we're going and what the terrain is like. If we are driving from one place to another and we have to stay on the roads, then we'll come up to a stop sign or whatever, turn left, then turn right. It's very much a rectangular coordinate system kind of idea. Would you agree with that? So we live on a sphere, on a spherical world, but we kind of live in a rectangular world. Where we talk about points, lines, and planes, and, straight lines, and, well, all lines are straight, but, when you're going down the road, especially if you look at like a downtown of most cities, their streets are very much rectangular, almost looks like a grid you can map something out on. Then as you go out from downtown, then the streets start to curve and whatnot. But we're talking rectangular coordinate system, okay? And so when we plot the points, here we go. Plotting points in space and defining functions is not much different than transportation examples. Up to this point, the only system you've learned has been the rectangular coordinate system, x, y, right? Also called the Cartesian plane, okay, or the Cartesian coordinate system. I want you to hear that word because if you are in a class, especially something with engineering, and your professor says something about the Cartesian coordinate plane, I don't want you to freak out and think everything's going to be really hard because that is the XY coordinate plane you've known forever. Okay? It just has a few names. All right. So an alternate way to describe points in space. So this is an alternate way to describe a point, any point. So we're not going to different points. We can go to the exact same points and we can use what's called the polar coordinate system. With polar coordinates, we do not use X and Y. Okay, it's much more like flying an airplane. So to define a point, we only need to state the angle of the point and the signed distance. Signed meaning positive and negative. Nobody's giving you an autograph. Okay, so we're going to rotate until we're facing the right way. So I'm going to show you how all of this works. So the polar coordinate system looks like a bunch of circles, and I know you don't even see a circle up here at all. But you don't necessarily always have to have the circles behind it. If I want to get to this point here, instead of doing what we're used to doing, which is we go to the right however much and then we go up however much, right? We go to the right X and up Y to get there. Instead, I would go to the right, whatever R is, and then rotate however much this angle is to end up in that point. Okay, so instead of walking and then turning a 90-degree angle and then walking again, we kind of walk out and then swing around, right? So that's how it's going to look on the coordinate plane. R being your radius of a circle, and then your ordered pairs, they're r theta, not x, y, okay? So in polar coordinates, it's defined by r theta. Absolute value of r is the radius of the circle. Theta represents the measure of the angle. So one really cool result of using polar coordinates is that the same point can be represented many different ways. What that means is this. If this point is, let's say, 4, 3. So I go to the right 4, I go up 3. That's literally the only way I can get there if I'm doing it on a rectangular coordinate system because we start at 0, 0. However, if it's in the polar coordinate system, since they're on circles, kind of like with the unit circle, we can rotate around an infinite amount of time, so there's different ways for me to get to that same point, much like we've been doing on the unit circle. Okay? All right, flip this over. And this is what a polar coordinate grid looks like, sort of. You won't always see what looks to you like the x and y axis because it's not the x and y axis. On the polar coordinate system, you have a polar axis. So this right here is your polar axis. This point right here, which we're used to calling the origin, we can still call the origin, but it can also be called the pole. So instead of having like two intersecting lines and having a positive, negative x, positive, negative y, we only really have what we consider like the positive x-axis. Now, I know you see other axes there. Sometimes they're drawn in there, but they don't have to be. And just like, kind of like we do with the unit circle, sometimes we might just draw that and do the polar type of thing on there without having to get all fancy, right? But let's look at how we're going to plot these. So I've got, this first point is 2 pi thirds. So that means I'm going to start at the pole. I'm going to go out to 2. Now I'm on that circle, and I rotate around on that circle till I get to pi thirds, and that's my point A right there. Okay? So at the radius, I went out to 2, rotated around to pi thirds. Everybody okay with that? All right, so put your pencil on where you think point B would be. You don't have to draw the point yet if you're not confident, but put your pencil on where you think it is. So then I'm here, I'd go out to 1, I'd rotate around to 3 pi halves, and I'm right there. And if you agree, go ahead and make your point there. That is point B. What questions you got? Okay, put your pencil on where you think point C is. Okay, so I go out to 3, which is the edge here. Go around to 4 pi thirds, which is right here. This is point C. And I want you to see a couple of things. That this is pi thirds, and they're only labeled in the first quadrant. They wouldn't even necessarily have to be labeled, but this is pi thirds. Then that same line that cuts through, that gives me my pi thirds angle in the third quadrant. So that's one way you can kind of line yourself up. And then I don't have extra. Somebody asked me why there was extra lines here. They're not really extra. It's just that they are split up. Like, what would this angle be, do you think? Pi what? Is it halfway between this and this? So what would it be? Pi 12ths. Okay, and that's not something that it can be used as a special angle. I mean, we don't usually do that, and nobody's going to ask you for that. But at the same time, you should be able to figure out, like, if this is pi 12ths, then wouldn't this right here be 11 pi 12ths? Because that would be 12 pi 12ths. You with me? Like, we can still reason around if we absolutely had to. So each little wedge in there is pi 12ths. But that's a little bit off topic, but somebody asked me about that earlier, so I wanted to make sure we talked about it. Okay, so then put your pencil where you think 2 negative pi 6 is. Right there. 2, and then we go around clockwise. That's D. Anybody have any questions at all? I'm about to give you, we're going to have a bonus one. This is a bonus, E. And it's going to be negative 2 pi thirds. Okay, so we have 2 pi thirds. We already did that one. Now, notice we have a polar axis. It's only like your positive x-axis. Technically, there's no negative for your x's, right? Which aren't really x's anyway. You have 2 options here, okay? I could start here and think about going out negative 2, even though it's not really negative 2, and then rotating pi thirds. That would work. However, another way to think about this is, well, it works, and it's not that bad if this is a very basic angle, but if this was like 5 pi thirds and I ended up somewhere else, like, it really could kind of make me adding and subtracting the angles be weird. So instead, what I suggest you do is we start off pretending like there is no negative. Let's just pretend like we're going to plot 2 pi thirds. So if I go to 2 pi thirds, I'm right there where A is, right? But because that's a negative radius, I am now going to go through the pole and end up on the other side right there. Okay? So when your radius is negative, not your angle, because we already did that, but when your radius is negative, you can put your pencil on where the positive would be. So if I went to 2 pi thirds, I'd end up right there. But since that's a negative radius, I go through the pole, stay on that same line, and put it on the other side. Okay? What questions you got? We good? I'll take that as a yes. All right. Let's look at this next example. Go ahead and plot point A for me. 2. And then let's make sure we agree. Excuse me? Okay, so 2 pi fourths. Are we good on that? Okay. So then 2 negative 7 pi fourths. I go to 2. I'm going to go clockwise. Where do I end up? Same spot, right? It's a different way to get there. So this is also B. Okay, so C is 2 9 pi fourths. Now, is 9 pi fourths, that's not an angle I know you know pi fourths, but 9 pi fourths, like we hadn't seen that a whole lot. If I do one full rotation, how many pi fourths is that? 8. So if I go to 2, I go around once, that's 8 pi fourths. I go one more pi fourths to get me to 9 pi fourths. I'm right there. That's C. They're all the same point. Let's see if D is. So D, negative radius. Remember, I'm going to pretend like it's positive. So I'm going to go to 2. 5 pi fourths puts me in the third quadrant. I push through the pole and end up, boom, right there. And D is in the same point also. So how many different ways do you think I could name that point? An infinite number of ways, right? So every point has an infinite number of names for it, basically. But in the rectangular coordinate system, there's exactly one. Okay? What questions you got? So it's just like the other concept of the unit circle where we can go around and around tons of times. Okay. Grab your other sheet of paper. So going on page 105 when we're done. And then this says, example 2 that we just did illustrates how a single point in polar coordinates can be expressed in many different ways. In fact, there are infinitely many ways that we could express any given point using polar coordinates. Okay? There's an infinite amount of them. All right, so for example 3, go ahead and see if you can plot the point that they gave us. Yes. Yes. All right, so 3, 5 pi 6, I think that puts me right there. Would you agree with that? Okay. So it says to plot the point, boom, we got that. Everybody good with plotting it? All right. Then we're going to write the polar coordinates in 2 different ways. We're actually going to do it in 3 different ways. So, all right, so I know that in order to get here, I went this way, right? I can also get here by going this way. Do you agree with that? And if I did, this would be 3, and what would my angle be? Negative 7 pi 6. Good. Because I would get, if I go from here, this would give me negative 6 pi 6, and then I got to go one more. Okay? So now I could keep rotating around and adding or subtracting 2 pi, but let's talk about a negative radius. That's fine. If I have a negative radius, then where I want to land is actually right here. Right? If the angle lands me there with a negative 3, then once I land, since it's negative, I go through and end up over here. You with me? So how can I get there? Okay, I heard 11 pi 6, and I think I heard the other one, but I heard some mumbling, so I wasn't sure. There's another one. Negative pi 6, I think I heard that over also. Now, those are the 4 ordered pairs between negative 2 pi and 2 pi. But they didn't give us any restrictions, and so there are an infinite amount of them. But if you don't have any restrictions, there's no use in getting crazy with it. Okay? But again, to get those negative radius, just go directly across from it and think, I want to land here. And if I land here, then since it's negative, I push through and end up over there. Okay? We okay with all that? What questions we got? Anything? All right. So let's connect rectangular coordinates to polar coordinates. All right, so here's our good old rectangular coordinates that we've known and loved forever. Let's say that my x value is the square root of 3 over 2, and my y value is 1/2. That means my ordered pair is square root of 3 over 2, 1/2, right? And that's how we know how to graph points. We go to the right, well, if it's positive, positive, which it is. But I would go to the right, turn 90 degrees, go up. Got a little right angle there, every time. Okay. All right, so then my polar coordinates, though, we're going to talk about the exact same point. So if I have this ordered pair, on your unit circle, this ordered pair corresponds to some angle. What angle is it? Pi 6. So theta is pi 6. Since these numbers are what they are, r is 1. So this ordered pair then would be 1 comma pi 6. And when we very first started the circle and we taped all those little triangles down, we basically had these side lengths. We came up with the ordered pair, and then we could see that these were the angles, right? But this point is in the this point right here, exact same spot as this point. But it is represented different depending on whether we're talking rectangular coordinates or polar coordinates. You with me on that? And then we just put it all together. This is the square root of 3 over 2. This is 1/2. This is 1. This is pi 6. And I can name this point in 2 different ways depending on what coordinate system I'm in. Okay, but I do want you to understand you're at the exact same point. And so some things are easier to plot in the polar coordinate system than they are the rectangular and vice versa. Honestly, this point, I feel like I'd have a much better chance of getting it accurate by graphing it in the polar coordinate system because this is what I have instead of this because I'd have to estimate both of those when I'm graphing. Does that make sense? So right now, you're not going to have to decide which one would be better. We're just going to see that sometimes one is better than the other. Okay. Flip that over then. So now we're going to convert. We're going to convert from polar to rectangular. I have my little right triangle here in the coordinate plane again. Using trigonometry, we know that this is theta, adjacent over hypotenuse, or x over r. That's cosine. Cosine is x over r. Sine is y over r. Right? Or just x and y if r is 1. And then if I solve for x and y by multiplying both sides by r, I get this. X equals r cosine theta, y equals r sine theta, just like your mg cosine, mg sine is in physics. We have done this before. We didn't relate it to polar because you didn't even know that was a thing at the time. We learned it. I taught it. You had an assignment over it. Then a lot of you just made up math on the test when it came to that. But here's something that's important. Whenever you are converting coordinates from one system to another, always sketch out the point first and check that your answer makes sense. That's important. Doesn't have to be a crazy, beautiful sketch. You'll see what we can do here. All right, so I've been given polar coordinates. These polar coordinates are r theta. Okay? I take a little xy axis. Even though it's polar, by doing that, just like I did with the unit circle, I never really drew a circle. We could just think circularly. So I would go out for this. I would go to the right 2, rotate around to pi, and I'd end up right there. So I'm just kind of putting a dot where that's where I would end up. That way, after I find it in my rectangular coordinates, I can make sure what I have makes sense. So I know from what it says over there, x is equal to r, which is 2, times cosine of theta, which is pi, and y is equal to r, which is 2, times the sine of theta, which is pi. So what is 2 times, what is cosine of pi? -1. So that gives me a -2. And then sine of pi is what? 0. So this is 0. So that means my ordered pair is -2, 0. And on the rectangular coordinate plane, if I start at 0, 0, and I go -0, that point makes sense. You agree with that? Questions? All right. So let's plot this one. 4, 5 pi thirds. What quadrant is 5 pi thirds in? 4th, and your pi thirds angles are closer to the y-axis, right? So if I went 4, 5 pi thirds, it would be kind of, well, sort of right there. Not necessarily that close, but I'm not going to redo it. It's good enough. So that means x equals r, which is 4, times the cosine of 5 pi thirds. And then y equals 4 times the sine of 5 pi thirds. All right, so you see if you can finish that one. Okay. I got 2, negative 2 square roots of 3. You agree with that? No? You got a question? Okay. On C, go ahead and put your dot where you think it goes so we can make sure we got that right. Oh, well, I didn't double check this one. Look, if I go 2 on a rectangular coordinate plane, if I start here, I go to the right 2 and down 2 square roots of 3, that looks about right. Okay. So put your point where you think it is for C. I would say it goes somewhere right about there. Think about it for a second if you're not sure, and then I'll talk you through it if I have to. Remember, it's a negative radius, so I'm going to start over here at 3, rotate to 7 pi 6, which is in the 3rd quadrant. It's a negative radius, so I go through the pole, and that's why I end up there. Okay? All right, so go ahead and find your ordered pairs. Or your ordered pair, rather. Mm-hmm. Okay. I was about to say, if nobody has any questions, I must say, one of the questions I always get, because I think I was starting to hear it back here too. All right. So we know in the end, this point ends up right here, right? But what we were given is 7 pi 6. And when I take the cosine of 7 pi 6 and the sine of 7 pi 6, the angle I end up with is actually in the 3rd quadrant. That's why both of these are negative. But see what happens when I multiply all this out, how these are both positive? That's why I end up in the 1st quadrant. Does that make sense? So even though you know you end up in the 1st quadrant, you have to actually use whatever angle they gave you there and think about what quadrant that's in. And then if I went to the right 3 square roots of 3 over 2 and then up 3 halves, yeah, it's positive. It's all good. Okay, so good question. I heard a couple of y'all start it. We're good with that then? Anything else? Okie dokie. So now we're going to go the other way. We are going to convert from rectangular to polar. Right? So I have this right triangle again. And we know that x squared plus y squared equals r squared. Now r kind of stands for 2 different things for us. R does mean the radius. And when we're talking about a unit circle, really any circle, the radius is always positive. But as we know, it is possible to have a negative r value. Okay, so it's really not the radius of the circle that's negative, it's the r value. And I know that can be a little confusing. But since we know this, I don't really care about r squared. I really want r. R is equal to plus or minus the square root of x squared plus y squared. And here's the thing. When we're solving these, or when we're converting, if they did not give us a domain restriction, like from 0 to 2 pi or whatever it is, then we can kind of have some options, because remember there's an infinite amount of ways I can write them. So the choice I think that is always good to make is to make the choice to just make it a positive radius. So even though, yeah, we could get a positive or negative out of this, depending on where we want to end up and what's happening, we can always just look at that as the positive one. Now, then we also know that tangent, so here's my theta, tangent is y over x, opposite over adjacent, right? Which means that theta is equal to the tangent inverse of y over x. And I skip this step a lot of times because it's just more to write. I mean, we still take the inverse, but we kind of take the inverse from here, which is fine. And once again, it says, whenever you're converting coordinates, always sketch out the point first and check that your answer is. It's important. Okay? So let's convert these. So I'm going to start with, all right. These are rectangular coordinates. So negative 2, 2, my point's going to end up right about there. Then I need it, so this is in x, y, and I need it in r theta. That's what I'm trying to get it in. So I'm going to say I know that r is equal to the square root of x, which is negative 2 squared, plus y, which is 2 squared. So that's the square root of 4 plus 4. So r equals the square root of 8. Now, can we simplify that? Yes. Here's what I know. If this was the calculus exam, I could tell you with 1,000% certainty that the square root of 8 would be perfectly acceptable. With the pre-cal test, I can tell you with about 99.9999% confidence, I'm pretty sure that's going to be fine. I haven't really, let me put it this way. I haven't seen anywhere where it wouldn't be fine. Because on this case, we're not testing whether or not you can simplify the square roots. You with me? So that's why I truly believe it would be fine to leave it like this. So I think it's probably better for us to leave it. I'd rather you leave it than try to reduce it and do that wrong and then miss the whole thing. You with me? So we're just going to leave it. If I find out anything else in the next few weeks, I'll let you know. But there's my radius. So then I know that the tangent of theta is equal to y over x. So that is 2 over negative 2, which is negative 1. All right, so we're still going to think through the first quadrant. What's your first quadrant angle that gives you a tangent value of 1? Pi fourths. So we are using a positive radius, and we want to end up in the second quadrant. So what is your second quadrant pi fourths angle? 3 pi fourths. So that means this ordered pair in polar coordinates is the square root of 8, comma, 3 pi fourths. Okay, we good with that? We're using Pythagorean theorem and tangent. Okay, so it's not getting crazy here. Any questions? All right, was a doobie. So this point is 1, negative square root of 3, somewhere right there. So r would be equal to the square root of x, which is 1 squared, plus negative square root of 3 squared. So that'll give you the square root of 1 plus what? 3. So that means r is equal to 2. Plus or minus 2, but even this would have been plus or minus. We're just going to go with the plus. Because then I have a positive radius and I want to end up in the fourth quadrant. Okay. So then I have tangent of theta is equal to negative square root of 3 over 1, which is just negative square root of 3. So let's think again through the first quadrant. What first quadrant angle gives me a tangent value of the square root of 3? Pi thirds. Good. So theta, but I don't want pi thirds. I want my pi thirds angle in the fourth quadrant. And what's the fourth quadrant pi thirds angle? 5 pi thirds. Very good. That means that ordered pair then is 2, 5 pi thirds. So you work on that last one on your own. Any questions? All right, so once you have an understanding of the polar coordinate system, you can save yourself from some work because we just converted 6 ordered pairs. We really only had to do work for 4 of them because if you end up with a point on one of the axes, right, like right here, 0, -5, so it's like a quadrantal, then clearly I know that my radius is going to have to be 5 and I'm going to have to end up here at 3 pi halves. Does that make sense? You can kind of reason through it that way. Or I could have done negative pi halves. That would have been fine too because they didn't give me any restrictions. Same thing up here. When I went to 2 pi and I ended up right here, in the rectangular coordinate system, if that length is 2, then I'm at -2, 0, like that right there. Okay? So when they're on the axes, they're very simple if you understand how the angles and stuff work. Okay? What questions we got? All right, so today we just learned how to plot the points and convert them. Tomorrow we're going to look at some cool graphs and get into some cool other stuff. I did want to show y'all this. I'm going to give you your assignment in a second, but this, I went next door and I grabbed this from Ackerman this morning. This is what he gave his BC kids yesterday. Okay? Literally, the first part, graph the following polar coordinates, which are almost the exact same coordinates we just did. So I'm telling you that because if you plan on taking BC next year, polar will show up about the same time it did this school year. If you're not taking BC or if you're a senior and you're going off to college, if you ever take Calculus 2, then you will see polar in there, but you can also see it in other classes, just letting you know that we're not doing it for nothing, like there is a connection there. Okay.